Hello, STT 315. This is Recitation 10. Our learning objectives are to construct confidence intervals for population proportion, construct confidence intervals for population mean, and compute sample sizes for mean and proportion given a margin of error. Task 1. A researcher finds that the average life expectancy for Bostonians is 78.1 years. He uses a sample of 50 Bostonians and assumed that the population standard deviation is 4.5 years. What is the point estimate for the population mean? At 90% confidence, what is the margin of error? And construct the 90% confidence interval for the population average life expectancy of Bostonians. So for finding the point estimate for the population mean, the point estimate for the population mean is just the sample mean. And we were given that the researcher finds that the average life expectancy for Bostonians is 78.1 years. That is the sample mean. So we get our point estimate to be X bar, which is 78.1 years. At 90% confidence, what is the margin of error? So since the population standard deviation is known, we were given that in the problem, then we can use the z distribution to calculate the margin of error. So we're going to use our critical value z star times sigma over the square root of n being the sample size. And so for 90% confidence, our critical value is going to be 1.645. And so our margin of error is going to be that z star value of 1.645 times our standard deviation, which is our population standard deviation, which is 4.5 years that was given to us. So we can plug that in here. And then our sample size, which our sample of 50 Bostonians, that is our sample size. So we were given this in the problem, and then we can use our table to find this or a calculator to find the critical value. And so we get 1.047 years as the margin of error. Construct the 90% confidence interval for the population average life expectancy of Bostonians. So we're going to take our point estimate, which is our X bar, plus and minus the margin of error. So we already found these components in earlier parts. So that's going to be 78.1 plus and minus 1.05, which we just found. So when you do that, the lower bound is 77.05 and the upper bound is 79.15. Let the following sample of 8 observations be drawn from a normal population with unknown mean and standard deviation. So here we have our sample of 8 observations, 22, 18, 14, and so on. And so first we want to calculate the sample mean and the sample standard deviation. So for calculating the sample mean, here I wrote above here what our sample was, which was given in our sample size. And so to calculate the sample mean, we're going to add up all the values in our sample and then divide it by the total. So once we do that, we get 160 over 8, which simplifies to 20. So 20 is our sample mean. And then to find the sample standard deviation, we'll take the square root of 1 over n minus 1 times the sum of xi minus x bar squared. And so our sample size is 8. So 8 minus 1 is 7 times the summation of our xi minus x bar. X bar here is 20 squared, and then we take the square root of that. So if you were to do this by hand, it would look like, well, you would sum over the different xi's minus 20 and square them. So you would have, for example, first we have 22 minus the mean, which is 20 squared, plus the next term, which is 18 minus the mean 20 squared. And then you would continue that for all the points till you get to xn, which in this case is x8. So that's 21 minus 20 squared. So this n in our example is 8. So this would be the sum I from 1 to 8. And so underneath the square root, that simplifies to 24. So if you take the square root of 24, you get 4.899, which is the sample standard deviation. Construct the 80% confidence interval for the population mean. So we're going to use a t-distribution because the population standard deviation is unknown to us. And so here are the components that we'll need. First, we need to identify how many degrees of freedom we have, which is n minus 1. So n again is 8, so that's going to be 8 minus 1, which is 7. And then we get a critical t value from a t-table, or you can get it from your calculator. And so here we have a confidence level of 0.8 or 80%, and then the degrees of freedom, which is 7. So we get a critical value of 1.415. And then for margin of error, it's calculated by our t star, which we just stated, times our S, our sample standard deviation, divided by the square root of n. And so if we plug in this information, we found S in part A. So that was 4.899 divided by the square root of 8 times this critical t value, which is 2.452. So that's the margin of error. So we're going to take our point estimate, which is the sample mean, which we found was 20, plus minus the margin of error. So we get the lower bound as 17.55 and the upper bound as 22.45. And this gives us an 80% confidence interval for the population mean. To construct a 90% confidence interval for the population mean, now our t star is going to change our critical value because now our confidence level changed. So now this is going to be t.9, but our degrees of freedom is still the same because our sample size is the same. So we get a different t star, which is 1.895, but our sample standard deviation stays the same. Our sample size stays the same. So our margin of error is going to equal 3.283. And so when we take our point estimate for the mean, so that's going to be our sample mean 20 plus minus the margin of error, we get the 90% confidence interval to be 16.72 to 23.28. And so what happened when our margin of error increased? Or what happened to the margin of error as the confidence level increased from 80 to 90%. So when that increased, our critical t star value increased. And because of that, our margin of error increases because you can see that you multiply the t star, you have t star times the sample standard deviation divided by the square root of n. So when your t star increases, the margin of error increases. And so when we have a larger margin of error, the confidence interval then becomes wider. So that's what happens when you increase the confidence level. A sample of 5,324 Americans was asked about what matters most to them in a place to live. 37% of respondents felt that good job opportunities matter most. So first, we want to construct the 90% confidence interval for the proportion of Americans who feel that good job opportunities matter most in a place to live. And so this information is given to us. We had our sample size of 5,324. This here is a large sample, so we can use normal approximation, meaning we'll use our z-star value from a critical value from the normal distribution. And so the critical value for a normal distribution for 90% confidence level is going to be 1.645. That's given in the problem there, our confidence level. And then we're also given our p hat in the question. So our p hat is 0.37 because we were given that 37% of respondents felt that good job opportunities matter most. So that's our p hat. 37% equals 0.37. So that's right here. And so to find the confidence interval, we need to have the point estimate, our p hat, plus minus our margin of error. Well, how do we find the margin of error? Well, first we need to find the standard error because we're going to take the z-star value times the standard error. So the standard error is going to be the square root of our p hat times 1 minus p hat over n. And so our p hat, like we said, is 0.37. So we can plug that into here and then divide it by the sample size, which is 5,324. So once you take the square root, you get 0.00662. And that gives us our standard error that we multiply by the critical value to get the margin of error. And then we take our p hat plus minus our margin of error to get a 90% confidence interval with the lower bound of 0.3591 and the upper bound of 0.3809. Construct the 99% confidence interval for the proportion of Americans who feel that good job opportunities matter most in a place to live. So here, it's pretty much the same setup, except now we're dealing with a 99% confidence interval. So our z-star is going to change. So you can get that from a table or your calculator, and that's going to be 2.576. And so now our margin of error is going to change. Our standard error is still the same, but our margin of error is going to be 2.576. So we get 0.01705. And so now we can take our p hat plus minus this margin of error. And so we get a lower bound of 0.3529 and 0.3871. That is our 99% confidence interval. And so which interval has a higher margin of error? Well, the 99% confidence interval has a larger margin of error than the 90% interval. A higher confidence level requires a wider interval to ensure greater certainty. And this is reflected in a larger critical z-star value, which increases the margin of error. What is the minimum sample size n required to estimate mu with 90% confidence if the desired margin of error is 1.2? The population standard deviation is estimated as 3.5. And then we want to talk about what happens if n if the desired margin of error decreases to 0.7. So here is the information that we're given. We're given the confidence level of 90%. So that means that our z-star value is going to be 1.645. We're given that the estimated population standard deviation is 3.5, and we're first given that a margin of error is 1.2. So the minimum sample size needed is going to be z-star times our estimated population standard deviation divided by the margin of error squared. So that's going to be 1.645 times 3.5 divided by our margin of error of 1.2, which gives us 23.02. But because we're trying to find the minimum sample size, we need to round up to the next whole number because we can't have a fraction of in a subject in a sample. So that's going to be, we round up to the nearest whole number. So that's going to be 24 is the minimum sample size needed. Now, if the margin of error, which was 1.2, decreases to 0.7, then our sample size is going to change. So the denominator, where the margin of error is going to now decrease to 0.07, which means our sample size is going to now increase to 67.64. Well, that's a decimal. We need to round up to the nearest whole number. So our sample is actually going to be 68. And so you'll see that when the sample size will increase when the margin of error decreases. That's because that's in the denominator. What is the minimum sample size n required to estimate p with 95% confidence if the desired margin of error is 0.08? The population proportion is estimated as p hat equals 0.36 from prior studies. And then we want to know what happens to n if the desired margin of error increases to 0.12. So we're given the confidence level of 95%. So that's going to be 1.96. And then we have our p hat, which is given to us as 0.36, and the first margin of error that we're dealing with is 0.08. And so our minimum sample size needed is going to be z star, which is 0.196, times the square root of p hat, 0.36, times 1 minus p hat, which is 0.64, divided by the margin of error, which is 0.08 squared. And so we get 138.26, but again, we're talking about sample sizes, so we need to round up to the nearest whole number, so that's 139. Now, if the margin of error increases to 0.12, where previously it was 0.08, that means we're going to have a larger number in the denominator. So we're going to have a smaller sample size, which is going to be 62. And so the sample size decreases when margin of error increases.